The question says, out of these two compound, which is more easily hydrolyzed by aqueous KOH? Okay, these two compounds are given there, and these two compounds are aryl halide, because you can see C6H5 C6H5 is given here, aryl halide. Okay, and it is talking about out of these two which one can easily get hydrolyzed. Always keep in mind, the rate of hydrolysis we determine based on the stability of carbocation. Higher the stability of carbocation, always remember, higher the stability of carbocation, higher is the tendency to get hydrolyzed. Okay, very simple concept. Higher the stability of carbocation, higher the tendency to get hydrolyzed. Out of these two aryl halide, the aryl halide which forms more stable carbocation will have a greater tendency to get hydrolyzed. Okay, based on this we are going to answer this question. Okay, so let's say we have a benzene ring. I can draw the structure of these two aryl halide. This is benzene ring, and this we have benzyl chloride is this is benzyl chloride. Okay, and next one we have, you can see benzene ring is there, benzene ring, and then we have CH, it is Cl, and here we have double bond. This is what we have. Okay, benzene ring. Okay, and these two are reacting with KOH aqueous, and here also it is reacting with KOH aqueous. What is the statement I have given? Higher the stability of carbocation, higher is the tendency to get hydrolyzed. So you can see carbon carbon. Here we have a carbon carbon. This is Cl and this is carbon. You can see Cl is more electronegative than carbon. It will pull electron density, hence it will carry positive charge and it will carry negative charge. Similarly, we are generating the carbocation, then we can check the stability. Cl is more electronegative than carbon. It will carry negative charge. It will carry positive charge is there. Okay, so you can see this is portion is what carbocation. Here also you can see this portion is what we have the carbocation. We can check the stability. Okay, pay attention carefully. You can see, if we see here, double bond, single bond, positive charge, conjugation is there. We have learned about the conjugated system, double bond, single bond, double bond, conjugation, double bond, single bond, positive charge, conjugation, double bond, single bond, negative charge, conjugation, double bond, single bond, lone pair, also conjugation is there. So you can see double bond, single bond, positive charge, conjugated system is there. And when the conjugated system is there, you can see resonance is there. We have the resonance. And so higher the resonating structure, so we have higher the resonance, we have higher is the stability. Okay, so based on the resonance we are going to find out the stability order, because we have the conjugated system. So we generated carbocation, but since this carbocation is you can see this carbon having the positive charge is a part of resonance, because it is generating the conjugated system. Here also you can see this carbon is having the positive charge, but this positive charge is a part of a conjugated system. Double bond, single bond, positive charge. This side also double bond, single bond, positive charge. If you see, you can see only one benzene ring causing resonance, and here we have two benzene ring causing resonance. So in this case resonance is very high. As we see, higher the number of resonating structure, higher the resonance, higher is the stability. So you can see in the second compound more resonance is there, that's why it is forming more stable carbocation. Okay, more stable carbocation is there, and if it is forming more stable carbocation, then it will have a greater tendency to get hydrolyzed, because to be in the stable state it will have very greater tendency to remove Cl, and as soon as this Cl is removed, OH will attach here. OH will attach here, so reaction will get completed. Okay, so statement is on, higher the stability of carbocation, higher is the tendency to get hydrolyzed. If you like this video, please share and subscribe to the channel.